So we left off yesterday before we started discussing inhibitors. This is the last topic of Unit 1. The first type of inhibitor that we are going to discuss will be reversible inhibitors. Reversible inhibitors will bind in a non-covalent fashion. They can be removed from an enzyme. So that is the idea behind, that is the definition behind a reversible inhibitor. If it is reversible, it can be undone. You can reverse the process. A competitive reversible inhibitor is an inhibitor that competes with the substrate for the active site of the enzyme. And you can reverse the inhibition of the enzyme. A non-competitive inhibitor will reduce the efficiency of the enzyme without affecting enzyme-substrate binding. So oftentimes this gets confused with allosteric inhibition. They are not necessarily the same thing. And this is actually an important distinction specifically for Cambridge. So oftentimes they will ask you for specific definitions to define something specifically or to name the type of inhibition. And if they give you a type of inhibition that is an allosteric inhibition, you need to say allosteric inhibition, not non-competitive. Or if they give you a type of non-competitive inhibition, you must be able to say that it is non-competitive. A non-competitive inhibition is a type of inhibition that reduces the efficiency of an enzyme without affecting the enzyme-substrate binding. So it does not affect the active site and substrate ability to bind to that active site. Allosteric effects are often equated with non-competitive inhibition. It is its own classification. Activators and inhibitors are both included as allosteric effectors. Allosteric effectors bind to a protein somewhere other than the active site and change the 3D conformation of the protein. It changes the overall 3D shape. And as we've discussed, the 3D shape is what determines the function of the protein. If a protein changes shape, it doesn't do its same job as when it had its original shape. The shape is what matters. The active site has a particular shape for a particular substrate. So, there is also a process called uncompetitive, as shown by this process here. Uncompetitive binds to the enzyme substrate binds to the enzyme substrate complex. But you're not really tested on that. Uncompetitive is simply that. It doesn't compete and it doesn't change the binding of enzyme substrate. Enzyme substrate binding has already happened. So it is not non-competitive and is not allosteric because the enzyme substrate complex has already formed. Allosteric and non-competitive both happen before the enzyme substrate complex has formed. Irreversible inhibition is just that. It cannot be undone. It is permanent. It will bind covalently to the protein with permanent effects. This is not the same thing as denaturing the protein. Denaturing the protein is changing its three-dimensional conformation in such a drastic way that it cannot change back to its original shape, either by making it too cold, too hot, too salty, not salty enough, too acidic, not acidic enough, too basic, not basic enough. Change the conditions too far in any direction, and you change the 3D shape too far so that it can't return to its original functional shape. You break it. You bend it too far and it snaps. or you bend it too far and the shoelace comes untied. You pull just a little too hard. That's denaturing. In irreversible inhibition, you bind another substance, an inhibitor, covalently to the protein, permanently altering its shape. You have not changed the shape of the protein by changing the environment. You have added something to it to change its shape and permanently bound that something. So this is competitive versus non-competitive. This is competitive. Here we have an enzyme, E, the substrate S, and the inhibitor I. The kinetic of the inhibition, the kinetics of the inhibition, or the constant of inhibition rather, Ki, is a reversible reaction as shown by the back and forward arrow. Shows and creates an enzyme inhibitor complex. Usually this is because the inhibitor has a similar shape to the substrate. A similar enough shape. Because the enzyme is the active site is designed to accept a shape, not a specific molecule, but a specific shape, which is recognized. A molecule is recognized by its shape. So something with a similar shape or a similar section of groups can be mistaken for it. So an inhibitor feels like the substrate and can therefore bind to the active site instead of the substrate. So here we have the enzyme inhibitor complex. Here is the inhibitor, and here is the enzyme. This is this part of the reaction over here. Here is the enzyme inhibitor complex. Here we have the enzyme and substrate reacting in a reversible reaction, forming the enzyme substrate complex, which typically will move forward in an irreversible reaction to create the enzyme and products. This is the reversible enzyme substrate part of that reaction. The product part is not shown here. So this section is shown here. Substrate enzyme, ES. Enzyme substrate complex, ES. Reversible reaction. This is the reaction moving to completion over here. That's all that competitive inhibition is. This is a chemical equation. This is a graphical image. This is showing the imagery of it. So this is non-competitive inhibition. An enzyme, a substrate, and an inhibitor, the same starting points that we had before. You have the interaction between the enzyme and the inhibitor. And you end up with the enzyme inhibitor complex over here. But you can still have interaction between the enzyme inhibitor complex and the substrate to form the enzyme substrate inhibitor complex over here. On the same fashion, you can have the enzyme substrate react to form the enzyme substrate complex over here, which can react to form the enzyme and product just as it could before. But the inhibitor is still around, floating around. And then you have the interaction between the enzyme substrate complex and the inhibitor, forming the enzyme substrate inhibitor complex again. And this cannot react. This cannot move substrate to product. This cannot convert substrate to product. Enzyme cannot convert substrate to product when the inhibitor is involved. This is the graphical representation. Enzyme and substrate react in a reversible fashion to create the enzyme substrate complex. This can move to completion. Enzyme and inhibitor can form the enzyme inhibitor complex. And this enzyme inhibitor complex can react with substrate to form the enzyme inhibitor substrate complex. The same way this enzyme substrate complex, if it doesn't move enzyme substrate complex substrate to product, this inhibitor can react with ES to make ESI. ESI cannot change substrate to product. That is how a non-competitive inhibitor works. It prevents the movement of substrate becoming product. Substrate cannot become product. Even though it can still bind to the enzyme, it cannot become product. An inhibitor can still bind to the enzyme at any time. It does not affect the ability of substrate to bind. That is non-competitive. They are not competing. There is no competition here. They are not competing. This is simply preventing anything from happening. It doesn't work anymore. So now that we understand those reactions, we need to move forward and understand how they'll affect our equation. The equations that we went over last time, the Michaelis-Menten plots. Since our Km, our Michaelis-Menten constant, reflects our enzyme affinity, how readily a substrate will bind to the active site of an enzyme, how readily how readily the enzyme substrate complex will form, how easily those two can fit together. An inhibitor that allows binding as normal but prevents the enzyme from actually functioning, which is a non-competitive inhibitor by definition, will only lower the maximum velocity of action, of enzyme activity. But the Michaelis-Menten constant will be maintained. The enzyme affinity is unchanged. Enzyme affinity is enzyme substrate binding readiness. An inhibitor that does not change how readily enzyme binds to substrate will not change Km. Non-competitive inhibitors will not change Km. They will lower Vmax because you are not moving substrate and changing it into product. You are not converting substrate into product. You are making that reaction slower. You are slowing it down. You are lowering the maximum velocity. An inhibitor that prevents a substrate from binding to the active site, effectively lowering enzyme affinity, will raise Km, because remember, the Michaelis-Menten constant, Km, is inversely related to enzyme affinity. A high Km means a low enzyme affinity. A low Km means a high enzyme affinity. So an inhibitor that prevents enzyme substrate binding lowers enzyme affinity, raising Km. Remember, Vmax is not tied to Km. If you keep adding enough substrate, Vmax can still be reached. Vmax is unchanged. This inhibitor that does this is a competitive inhibitor. A competitive inhibitor will raise Km and leave Vmax unchanged. Vmax will be unchanged and Km will be raised by a competitive inhibitor. This is also why we make the distinction between non-competitive and allosteric. Because allosteric affects whether or not substrate will bind to enzyme. Allosteric changes the shape of the active site. If the shape of the active site changes, the substrate cannot fit. If the substrate cannot fit, then the active site has a lower affinity. So an allosteric inhibitor will lower enzyme affinity, thereby raising Km and lowering maximal velocity by inhibiting enzyme substrate complex formation and therefore the progress of the reaction. So allosteric inhibitors have a different effect on enzyme kinetic equations than non-competitive inhibitors. That's why Cambridge needs you to make the distinction. Not just definitionally, but graphically as well. So this is the graph. This is the normal Michaelis-Menten plot with no numbers. There are no numbers here, so you can't say high Km, low Km. You can't make that distinction without any real numbers. And you can't say high or low without two things to compare. Because the number 8,000 could be high or it could be low. If you compare it to 9,000, it's low. If it's over 9,000, then it's Goku. Yes, I know. I said I wouldn't make as many jokes during these review sessions. I lied. That's not the first time. It won't be the last. So, a normal enzyme Michaelis-Menten plot is this black line. A competitive inhibitor has the same Vmax as substrate concentration increases. You can reach Vmax. But Km, which is 1/2 Vmax, the substrate concentration at 1/2 Vmax, y equals 1/2 Vmax, x equals Km. The x value at 1/2 Vmax is higher than the Km of the black normal enzyme. This one, the 1/2 Vmax, is here. So here is the Km for the black line, here is the Km for the red line. The Km is higher. It raises Km. Higher Km, lower enzyme affinity. For a competitive inhibitor, same Vmax. The blue line is a non-competitive inhibitor. It prevents the reaction from going forward, but it does not change the affinity of substrate to enzyme active site. So Vmax is lower. Vmax is here in the black line and here in the blue line. 1/2 Vmax here is about here. That makes it that number right there. And there versus there. They have the same Km. Their Km value is the same. The blue and the black lines' Km values are the same. The Vmax is different, Km is the same. The enzyme affinity is the same. Their Vmax is different. That is a non-competitive inhibitor. If an allosteric inhibitor were in play here, both of these numbers would change and both of them would be different. It would be some combination of the two. It would be like in between these two things. That's what it'd end up looking like. It would be weirder looking. So you shouldn't be expected to estimate that look. But you should be able to explain what's going on. If they told you to describe and explain a graph, your explanation would be the allosteric inhibitor is affecting the shape of the active site of the enzyme, changing the affinity of the enzyme, therefore therefore changing the Km value, and it is preventing the reaction from proceeding, therefore lowering the maximal velocity of enzyme activity. So both Km and Vmax are affected in an allosteric inhibitor. Understood? That's an explanation of what's going on. A description is Km is different